Welcome to the deep dive. Today we're tackling something that's, well, everywhere. Optimization.
Hmm.
It's basically just finding the best way to do something, right? Like the fastest route to work or cramming everything into a suitcase.
Exactly. We all do it. And in AI, specifically deep learning, it's absolutely fundamental. It's how we train these neural networks.
Training them. How?
By tweaking their internal settings, we call them parameters or weights. The goal is to get the network's predictions as close as possible to the actual data. Think of tuning an instrument.
Okay. Trying to get the best sound or the best prediction, you minimize the errors.
Right. We have this thing called a loss function
Oh.
that measures the error. Optimization is all about driving that loss down, ideally towards zero.
Makes sense. We always want the best result, but here's the twist we're exploring today. Can you try too hard? Can you optimize too much?
That's the core question. It sounds counterintuitive, but yes, sometimes overdoing it can lead to problems. It can backfire.
Right. Like, why did the over-optimized programmer quit?
Oh boy, why?
They spend so much time fine-tuning their code for microsecond improvements, they forgot the deadline was yesterday.
Huh.
Yeah.
A classic case of missing the forest for the trees. So yeah, today we'll unpack optimization in deep learning, look at these pitfalls of, well, over-optimization, and why getting the balance right is so crucial for AI's future. We've got some great source material to guide us.
All right, let's dive in. So, fundamentally, why is optimization such a big deal in deep learning research?
Well, it's the engine, really.
Yeah.
Without it, we can't teach these complex networks anything useful. It's how they learn.
And it's not always easy, you mentioned.
Not at all. Theoretically, it's fascinating because neural network optimization problems are usually non-convex,
Non-convex, meaning?
meaning the landscape we're searching through isn't a simple bowl shape with one lowest point. It's more like a mountain range with lots of valleys, local minima, where you could get stuck.
Okay, so finding the absolute lowest point is tricky.
Exactly. But the surprising thing is, we often do find really good solutions anyway. It's like these neural network problems are a special class, maybe beyond traditional convex optimization, kind of like how canonic optimization opened up new types of solvable problems.
So what makes it so complex specifically with neural nets?
It's the structure. You've got layer after layer of these nonlinear functions all connected. Changing something in one layer can have unpredictable ripple effects way down the line. It's
Ah.
complex.
Like a giant interconnected Rube Goldberg machine. Okay, one source mentions three key parts of supervised learning: representation, optimization, and generalization. Where's our focus?
Today, it's squarely on optimization. Representation is about what the network can learn, its capacity. Generalization is how well it performs on new data it hasn't seen. Optimization is the process of finding the best settings during training.
Got it. And there's some different terminology, right? Classical optimization versus deep learning.
Yeah, but just slightly different words for similar ideas.
That is.
What classical folks call the optimization variable, we call a weight or parameter.
The knobs we're turning.
Right. Their objective function is our training loss.
The score we want to minimize.
Exactly. And their step size is our learning rate.
How big a turn we make on the knobs each time. Okay, same concepts, different names. So how do we actually minimize this training loss? What's the main tool?
The workhorse algorithm is gradient descent, or GD.
Gradient descent sounds directional.
It is. Imagine you're on a hillside in thick fog, and you want to get to the bottom. What do?
Feel for the steepest downhill slope and take a step.
Precisely. That's gradient descent. It calculates the gradient, which way is steepest downhill in the loss landscape, and takes a small step in that direction, adjusting the network's weights. Then it repeats.
Okay, step by step, heading downhill. But how does it know which way is downhill in this, like, million-dimensional space of weights?
Ah, that's the magic of backpropagation, or BP.
Back propagation. Heard of it.
It's a super efficient algorithm for calculating that gradient, the downhill direction, for every single weight in the network, all at once. Its invention was a massive breakthrough.
How does it work, briefly?
It involves two passes. First, a forward pass. Data goes in, flows through the network, and we get a prediction.
Okay, the guess.
Then, a backward pass. We look at the error in that guess and propagate it backward through the network, layer by layer. This backward pass cleverly calculates how much each weight contributed to the error.
So it figures out who to blame for the mistake?
Sort of, yeah.
Yeah.
And that blame tells us how to adjust each weight to reduce the error next time. Those adjustments are based on the gradients calculated by backprop.
Forward to guess, backward to learn. Makes sense. So if we just keep following the gradient, are we guaranteed to find the absolute best solution, the global minimum?
Not necessarily. Basic GD theory tells us that if the landscape is relatively smooth, technically, Lipschitz smooth, and we pick our step size, the learning rate, carefully,
Hmm.
we should eventually reach a point where the gradient is zero, a flat spot, a stationary point.
Okay, sounds good. Flat means we're at the bottom.
It could be the bottom, the global minimum. Or it could just be a local minimum, a smaller valley. Or even a saddle point, flat in some directions but not others. So no guarantee of finding the absolute best spot.
The dreaded local minimum, right. So what other challenges pop up, especially with deep networks? Lots of layers.
A really big one is the vanishing and exploding gradient problem.
Vanishing and exploding. Sounds dramatic.
It can be. Think of that backward pass during backpropagation. The error signal gets passed back layer by layer.
Okay.
If, at each layer, the signal gets multiplied by a number slightly less than 1, by the time it gets back to the early layers, it can become incredibly tiny, essentially zero, vanished.
To the early layers, stop learning.
Pretty much. They don't get a meaningful signal about how to adjust. Conversely, if the signal gets multiplied by numbers bigger than 1 at each layer,
It blows up.
exactly, it can become enormous explode, leading to huge, unstable updates to the weights. The whole training process can just go haywire.
Wow, so it's like a message getting distorted as it passes down a line.
That's a great analogy. Our source material shows a simple math example, FWO W712. If you plot that,
Yeah, figure 1, I see it.
you see those really flat areas? That's where gradients vanish. Learning is painfully slow if you start there. And see those super steep cliffs?
Yeah, almost vertical.
That's where gradients explode. Makes things very unstable. There's a nice basin around the solution, W1, where things work well. But getting there from the wrong starting point is tough.
So these aren't just theoretical worries, they really mess up training.
Absolutely. Slow convergence, maybe never converging properly.
Yeah.
Instability makes it really hard to pick a good learning rate. It's a major hurdle.
Okay, so we have this potentially treacherous landscape,
Right.
flat plains, steep cliffs, local valleys. How do people actually manage to train these deep networks? What are the tricks?
Right, there are quite a few tricks of the trade that have been developed. One basic but important one is careful initialization.
How you set the weights at the very beginning.
Exactly. Choosing good starting values can help avoid those nasty, vanishing, or exploding regions right from the outset. Gives you a better chance of landing in a nice part of the landscape.
Like starting your hike on a clear path instead of in a swamp. What else?
Batch normalization, or batch norm, is a huge one. Very widely used.
Batch normalization, what's it doing?
It basically recenters and rescales the activations, the outputs of intermediate layers within the network. It does this across a small batch of training examples.
Why? What does that help with?
Well, the original paper claimed it reduced internal covariate shift, a kind of instability, but more recent thinking suggests its main benefit is actually smoothing the loss landscape.
Smoothing the landscape, like making the hills gentler.
Yeah, making the gradients more predictable, less erratic. It helps stabilize training and often allows for higher learning rates.
Sounds useful. Any downsides?
It does depend on the statistics of that mini batch being representative. If your batches are too small or not random enough, it might not work as well, or could even hurt performance sometimes. That's led to other methods like layer normalization too.
Okay, so initialization, normalization. What about the network design itself? Does architecture matter for optimization?
Hugely. There was a big push towards deeper and deeper networks, thinking more layers meant more power. But people hit a wall. Even with good initialization and batch norm, training plain networks beyond 20 or 30 layers was really, really hard.
Gradients still vanishing.
Yeah, seems like it. Then came a major breakthrough. Residual networks, or ResNets.
Ah, ResNets. Heard that name a lot. What's their secret sauce?
It's deceptively simple. Skip connections.
Skip connections.
Yeah, instead of a layer just transforming its input, a ResNet block also adds the original input back to the output of the layer, essentially letting the signal skip over the transformation if needed.
So it creates like an express lane for the gradient signal.
That's a perfect way to put it. It allows gradients to flow much more easily through many, many layers without vanishing. This let people train networks with over 100 layers, even 152 layers, achieving state-of-the-art results.
Wow. So changing the wiring diagram at the network made a huge difference.
Massive difference. And that sparked tons of research into other architectures, like dense nets, and even automatically searching for good architectures, neural architecture search.
Okay, architecture is key. What about managing the learning rate during training? You mentioned that step size earlier.
Right. Learning rate schedules are critical. Most people use stochastic gradient descent, SGD, in practice.
Stochastic, meaning Random.
It means using small, random batches of data, mini batches, to estimate the gradient at each step instead of the whole data set. It's much faster. But how you set the learning rate for SGD and how you change it over time really matters.
So you don't just keep it constant.
You can, and sometimes that works fine. But often you use a schedule, like stepwise decay. Start with a certain rate, then reduce it by, say, 10x after a certain number of training steps, then maybe again later.
Okay, gradually slowing down the steps as you get closer.
Exactly. There's also a warm-up phase some people use. Start very low, then increase the learning rate over the first few thousand steps. And even fancier things like cyclical learning rates, where you oscillate the rate up and down.
Seems like there's a lot of tuning involved there.
Definitely an art to it. Which leads to another category, adaptive gradient methods.
Adaptive, how so?
Methods like AdGrade, RMS Prop, and the really popular one, Atom. These algorithms automatically adapt the learning rate for each individual weight in the network.
Whoa, each weight gets its own learning rate.
Effectively, yes,
Yeah.
based on its past gradients. AdGrad, for example, lowers the rate for weights that get updated frequently and keeps it higher for ones that update rarely, good for sparse data.
And Atom, why is it so popular?
Atom combines ideas from RMS Prop and another concept called momentum. It often works pretty well out of the box with less manual tuning of the learning rate, and it tends to make rapid progress early in training.
Sounds great, like an automatic tuner for every parameter.
It often is. Though interestingly, some research finds that very carefully tuned SGD can sometimes lead to models that generalize better to new data than Atom, even if Atom converges faster initially.
Huh. So faster isn't always better in the long run.
It seems that way sometimes. And there were even theoretical issues found with RMS Prop and Atom initially, which led to fixes like AMS Grad. It's still a bit of a mystery exactly why they work so well in practice, but they're incredibly useful tools.
Okay, this landscape of tricks and techniques is fascinating, but it also feels like this constant push for better, faster optimization. Which brings me back to that idea of over-optimization and the AI dilemma people discuss online. How does this connect to huge models like LLMs?
That's a really interesting connection people are finding. The discussion is basically asking, are current methods for training LLMs, pre-training, fine-tuning, alignment with human feedback, hitting a wall?
Hitting a wall, how?
The argument is that maybe we're optimizing these models so intensely on their training data and alignment tasks that they're becoming brittle. They might be reaching a saturation point for the current ways we train them.
So, getting diminishing returns from just doing more of the same optimization.
Potentially, yes. And one specific concern raised is this idea of models needing huge amounts of computation time at inference when you ask them a question, maybe up to an hour for complex tasks.
An hour for an answer, wow.
Yeah. People are framing this as a kind of test time optimization where the model isn't just retrieving info, but doing intensive computation to generate the best possible answer based on its training.
But, like one commenter said, time is money. An hour-long wait isn't practical for most things.
Exactly. It drastically reduces the usefulness. It's like we've optimized it so much for theoretical best answer quality that we've broken its practicality.
And there was an analogy about driving a car.
Right. If you train someone intensely on a specific simulator, but they have zero real-world driving sense, would you expect them to drive intuitively? The idea is maybe LLMs optimize heavily on specific data, lack the broader common sense to handle tasks that deviate even slightly.
Optimized for the simulator, useless on the actual road.
Kind of. The suggestion is maybe current methods are just a dumb day zero bootstrapping approach. Maybe future AI needs to grow or learn more dynamically, not just be these optimized but ultimately frozen brains.
And this connects to when LLMs sometimes just make stuff up. Confidently.
It could be related. One user described it like having a stone meth head babbling with full seriousness about things that are not there. If the optimization focuses solely on predicting the next likely word or mimicking human conversational patterns,
It might learn to sound confident even when it's totally wrong.
it's plausible. It prioritizes pattern matching over actual understanding or grounding in reality.
Which reminds me of another joke. Why did the over-optimized LLM give terrible advice?
Why?
Because it calculated the statistically most probable advice based on internet forums, which was usually dump them, or have you tried turning it off and on again?
Huh. Perfectly optimized for mediocrity, perhaps. It really highlights this tension.
Definitely. So stepping back a bit, what have researchers learned about the overall shape of these optimization landscapes for neural nets, beyond just local minima?
Well, despite the theory predicting difficulties, empirically, deep learning often finds good solutions. When people have tried to visualize slices of these high-dimensional landscapes, they sometimes look surprisingly manageable, not riddled with terrible traps.
So maybe not as scary as the theory suggests.
Perhaps not always in practice. There's this idea of mode connectivity, that different good solutions, different valleys in the landscape, might actually be connected by paths that don't go over high mountains.
Yeah.
You could potentially travel between good solutions relatively easily.
Interesting. So maybe the good solutions aren't isolated islands.
Maybe not. And then there's the lottery ticket hypothesis.
Lottery ticket.
Yeah, the idea that within a large, randomly initialized network, there exists a smaller subnetwork, the winning ticket, that if trained in isolation from the start, would achieve similar performance to the full network.
So you don't necessarily need the whole huge network, just the lucky part.
It suggests that maybe over-parameterization helps find these lucky tickets, but isn't strictly necessary for the final performance itself. It hints that optimization might be finding these efficient subnetworks. There's also evidence that wider, flatter minima in the lost landscape tend to generalize better to new data than sharp, narrow ones.
Wider valleys are better than narrow canyons. Makes intuitive sense for robustness. What about theory, trying to explain all this?
There's ongoing theoretical work. People have analyzed simpler cases like linear networks or extremely wide networks. One big area is the neural tangent kernel, or NTK. Under certain conditions, particularly with very wide networks, NTK theory shows that the network's learning process behaves much like a simpler linear model during training. This makes the math much more tractable and helps explain why optimization can work so well, at least in those regimes.
So theory is catching up to practice, trying to explain why these optimization methods, despite the challenges, often succeed.
Exactly. It's a continuous interplay between practical tricks, empirical findings, and theoretical understanding. Many deep learning optimization methods are adaptations of classical techniques, but tailored for the unique scale and structure of neural networks.
Okay, let's try to wrap this up. What's the big picture takeaway from this deep dive into optimization and its potential dark side?
I think the main point is this tension. Optimization is absolutely essential. We need it to train AI. But chasing the absolute mathematical minimum of our training loss, pushing every optimization trick to its limit, isn't always the best strategy.
It can lead to diminishing returns or even make the model worse in real-world scenarios.
Precisely. Over-optimization can lead to brittle models that don't generalize well, or systems that are theoretically optimal but practically useless, like that hour-long response time example.
And the AI dilemma suggests maybe we can't just keep scaling the current optimization paradigm forever. We might need new ideas.
That seems to be the growing sentiment in some circles. Simply making networks bigger and optimizing them harder with the same fundamental techniques might not get us to the next level of truly flexible, adaptable intelligence. Understanding these optimization nuances helps us see past the hype.
Right. It's not just about making the loss number go down. Okay, here's a final thought for our listeners. As AI gets more powerful, how do we navigate this? How do we strike that crucial balance between optimizing for performance on known tasks and building systems that are truly robust, adaptable, and, well, intelligent in a broader sense?
That's the million-dollar question, isn't it? Finding that sweet spot is key.
Definitely something to keep thinking about. Thanks for joining us for this deep dive.